Example 4. At any instant, the horizontal position of a weather balloon is given by this, where t is in seconds. If the equation of the path is this here, determine the magnitude and direction of the velocity and acceleration when t equals 2 seconds. All right, so we want to find the magnitude and the direction for both the velocity and the acceleration at t equals 2 seconds. I'm going to do parts of this a couple different ways. So let's start with the velocity. Maybe we should draw a little picture too. So here's your plane, and then this here, this is the path of the weather balloon. So something like this, and here's your weather balloon up here. I'll just draw a circle for that, but that's the idea. All right, so we're going to get started with the velocity, and we're actually going to have to find the velocity component in the x direction and also in the y direction. So I'm going to start with the component in the x direction first. Okay, so I'm going to need v sub x, and you can think of that as x dot, and basically it's the derivative of x with respect to t. So I need to find the derivative with respect to t of this over here, 6t, which is just 6. Okay, so I have right now the velocity component in the x direction is 6 feet per second in that direction. Okay, now I'm going to go ahead and find the velocity component in the y direction. All right, so I need v sub y, which we can think of as y dot. It's the derivative of y with respect to t. And right now I have this here. So I'm going to go and use that. So I want to take the derivative of this x squared over 2, but I want to do it with respect to t. So our variables aren't matching up, so we're going to use a chain rule in this case. So I'm going to take the derivative, the ordinary derivative first. So that just gives me x, and then I'm going to chain on dx dt. All right, so you can think of it a couple different ways. You can think of this as x times x dot, right? That's what dx dt is, first time derivative. And you can also think of this as x times v sub x. Okay, so when t is equal to 2 seconds, x, I'm going to have to use this equation up here again, is equal to 6 times 2, or 12, and v sub x, which we just found a little earlier, is equal to 6. So then v sub y is going to be equal to, just using this right here, it's just going to be equal to 12 times 6, or 72 feet per second in the upward direction. Now, if you didn't like what was going on here with the chain rule, I can give you a little bit of an alternative. So I'm going to do that next. All right, so I'm going to write this as a note. But basically, if I want another way to find this so that maybe I didn't have to use the chain rule, I can. And what I'm going to do is take this here and use it to rewrite this equation here so that it's y in terms of t. So I'm going to take this, since x is equal to 6t, I'm going to take the 6t, plug it in for this x here. So y is going to be equal to 6t squared over 2, or 18t squared. So then if I want to find the velocity in the y direction, all I have to do is take the derivative of y with respect to t. So I'm taking the derivative of this. So that equals 36t. And then at t equals 2 seconds, this velocity in the y direction is going to be equal to 72 feet per second upward. So you get the same answer. All right, so now I want to finish up by finding the magnitude and the direction for this velocity. So the magnitude of velocity at t equals 2 seconds is v, which is going to be equal to the square root of the sum of the components squared. There's our formula, so I'm just going to go ahead and plug in. This here was 6, and this was 72. And that basically is equal to 72.3 feet per second. And now we're going to go ahead and find the direction of the velocity at t equals 2 seconds. And this is going to be equal to theta. I'll use subscript v here. And that's equal to the inverse tangent of v sub y over v sub x. And that's about 85.2 degrees. So basically this is your path, that's the weather balloon. That's the velocity at 2 seconds, and this here is the angle. All right, so we found the magnitude and the direction of the velocity, and now we have to go do that for the acceleration. All right, so we're going to go ahead and do the acceleration. So I'm going to start with a sub x. So basically I need to take the derivative of v sub x. But from earlier we saw that v sub x is equal to 6. So when I take the derivative of 6 with respect to t, I just get 0. And then we need to find a sub y. So I need to take the derivative of v sub y with respect to time. So I'm going to go ahead and do that. And earlier we saw that v sub y is equal to x times v sub x. So I have a product here, so I'm going to use the product rule. So I'm going to keep x as it is and take the derivative of v sub x. I'm going to have d v sub x over dt. And then I'm going to add on, keep v sub x and take the derivative of x with respect to t. So I went ahead and used product rule. Now x is fine, I'm just going to leave that as is. When I take the derivative of v sub x though, I already did that earlier, that's just 0. That's what I have up here. So I have 0 there. And then v sub x, that was just 6. And then when I take the derivative of x with respect to t, that's this over here, that's just 6. So that's equal to 36 feet per second squared, and it's in the upward direction. Let's just put a little arrow there. Now, if you don't like what I did here with the product rule, there is an alternative way, so I'm going to make a little note here like I did earlier. So if I want to find a sub y and I don't want to use the product rule, then this is how I'll do it. From the last note I made, we found v sub y and it was 36t. So it was in terms of t, so then I just take the derivative like I normally would, so I just get 36. And then this is feet per second squared, and I get the same answer. All right, so now I'm going to finish up this problem by finally finding the magnitude and the direction of the acceleration. So magnitude of acceleration at t equals 2 seconds is, I'll write down the formula here, and then we'll just plug those values in. Well, that one was just 0, and this other one was 36 squared. Well, we just get 36 feet per second squared. So that's the magnitude. And then the direction of the acceleration at t equals 2 seconds is theta, and I'll use subscript a here, equals inverse tangent this is 36 over 0, which is just your 90 degrees. Okay, so that finishes up this problem, but I do want to make one more final note. So in the previous examples, we were using vectors. But if this is your position vector, x and y, they're functions in terms of t, so you can think of them this way. And then this was given, it's right here, so that's 6t. And we had actually found this, and that was 18t squared. So if you wanted to, you could do example 4 the same way we did the first 3 examples using vectors if you wanted to.